Okay, here we are at the physics video lecture, Physics 107B video lecture 10. So today I'm just going to wrap up some of the discussion from last time and then work a homework problem that people were interested in seeing. And it's a good point to bring up some homework problems before they're too far in the past. So if you have any questions, let me know. But picking up where we left off, we had our monochromatic waves. I'm going to try to draw a nice drawing here that I can refer to. So we're in the Z direction, we have X and Y, and we had our electric field and the accompanying magnetic field in phase, perpendicular to each other, and we can give them colors just because we can. So we would have the E field here, and then the B field perpendicular to it. So good. These are our monochromatic waves that I'll write down again. That were, yes. So the complex form, we'll go ahead and write down. We have E tilde of R and T equals E0 tilde E to the I K dot R minus omega T. And in n hat direction, in this case right here, n hat is in the direction of x hat, right? And of course it's propagating to the right. The magnetic field, also complex, R and T, E0 tilde E to the I K dot R minus omega T. Now the direction here, the K hat is in the direction of propagation. So if I write K hat cross N hat, and you look right here, K hat crossed into N hat, so Z hat crossed into X hat is coming out of the board. Okay, so that's right. Also, generally, we have magnitude E divided by C. And we're also going to make use of the fact that omega is equal to CK. So K hat, of course, is a unit vector. K is the wave number. And we're going to make use of the fact that C squared equals 1 over mu naught epsilon naught in the diverse transformations that follow. Good, so using this, we'll start with the energy density. So good. Like to number things, so we have our energy density. So energy per volume, U, and we had this in the past, 1/2 epsilon naught E squared plus B squared over mu naught. Okay. But now we have this relation here. Get a better pen. We can replace the B with E in this manner. And so the form that we're going to use is U is equal to epsilon naught E naught squared cosine squared KZ minus omega T plus delta. So what I've done here is gone to the real part, obviously. Okay, so I've gone to the real part because I want the actual real proper dimensions and everything. Good, so I've gotten to the real part, and we'll hold on to this. That's the energy density. Then we have the Poynting vector. And we know its definition, S is equal to 1 over mu naught E cross B. So let's inspect that before we evaluate it. So E cross B is clearly, with your right hand rule, pointing in the direction of propagation of the wave. Okay, it's going to be our energy flux, so that's an important one. And it is a vector. And doing the same thing I've done here, we're going to have S is equal to C epsilon naught E naught squared cosine squared KZ, that's a K, minus omega T plus delta. So we've got the real parts. And this, of course, is in, as I just stated, in the Z hat direction. So we have that. And we want, in addition to that, the momentum. So we have momentum. And this one I'll just put in the form, that was that cursive momentum vector we had. And we can express it in terms of the energy density, but it's a vector, it's also in the Z hat direction. Because it's actually defined in terms of S. This is S vector. Okay. So momentum and this energy flux, of course, in the same direction. Good. So we can, of course, also define these things. I'll just put this as a note. These are the oscillating quantities, okay, with your cosine squared. So average values, you average over a period of the cosine squared, or as many periods as you want to average over, and the average of the cosine squared is known to be, is well known, right? It's 1/2. So then we can put these things in square brackets. So time averages are these same expressions here. Get rid of the cosine squared and just 1/2. Okay. 1/2 epsilon naught E naught squared, and time average of that vector. It's still a vector, by the way. 1/2 C epsilon naught E naught squared. Finally, I want the intensity and the radiation pressure. I'm running out of room here. Let's see. So intensity which is power per area, that is just the magnitude. Okay, so the intensity is just the magnitude of the Poynting vector, and we're going to do an example with the. Let me write that down first. With the solar constant. Okay. And what we can do is we can divide this by the speed of light, and we have a pressure. Okay. In fact, if you do your dimensional analyses on these things, you'll see these are very basic. Okay. So that's what I want to end with as an interesting numerical thing here. I'll just use this space right here. So we have pressure, right, P, right, that would be force per area, or it would be energy per volume, multiplied both by length, okay? So you've got that right there, okay? Energy per volume. And that's intensity divided by speed of light. So this interesting numerical, so P pressure is equal to intensity over C. Now the interesting example is just our sunlight that we're bathed in, okay? It's called the solar constant. Over the speed of light. So that's an interesting example because this is a well-known quantity, and as is the speed of light. So if we go ahead and plug in the 1340 watts per square meter divided by the speed of light, 3 times 10 to the 8 meters per second, we get roughly, what do we roughly get? Roughly 4, a bit more than 4. I'll just write approximately 4 times 10 to the minus 6 Pascal. Okay. So that's just the pressure that we get from sunlight at noon. And you want to compare that to something to see what it means, and you remember the atmospheric pressure is about 10 to the 5 Pascal. So that's separated by 10, 11 orders of magnitude. So I'll just write here, note, P atmosphere is equal to 10 to the 5 Pascal. So yeah, the radiation that we feel every day exerts some pressure, but it's a very small amount. Good, so that's going to wrap up a certain section. What we're going to do in the wave theory coming up is pursue the waves not in vacuum but in matter, and then try to derive the basic laws of optics. Okay, so that'll be coming up next. But before we go there, let's go back to some of our older problems while they're still reasonably fresh in our minds. So yeah, like I said, our next task is to do some of the stuff we've learned about in optics. We're going to derive Snell's law, laws of reflection, partial transmission, transmission coefficients, that kind of thing. Okay, but now we're going back to chapter 7. So returning to chapter 7, where we were just putting together Maxwell's equations. So before we had the wave equations, we have an interesting particle of a problem of a particle in circular motion. So this was a homework problem. So we've got a positive Q, think like a proton, and we have circular motion around it of a negative Q. So we're just talking about the attraction, Coulomb's law. So we have a circular orbit of a charged negative particle like an electron around, say, a proton. Good, so we've got the circular orbit, and what we're going to do, I'll kind of number what happens here. Second thing that happens is we dial in a B field. So we introduce a B field here. So introduce B. now we have, in addition to Coulomb's law, we have the magnetic force of a charge moving in a B field. Okay. And this is a minus charge, and we're doing the directions I'm indicating, so we're going to get an additional force towards the center. This thing, positive Q, is just occupying the center. So we're going to get an additional force. And on the other hand, we're going to have a problem with Faraday's law, because this orbiting charge acts as a current, okay? So we'll have Faraday's law as well. And the interesting result that follows is that these two contributions, the contribution from Faraday's law, as well as the contribution just from this magnetic field, leave the radius of orbit unchanged. So prove that the orbital radius is left unchanged. Orbital radius is left unchanged. And it's an interesting argument how that comes about. So what we do is we'll start with Coulomb. I'll just number my steps as we go here. So initially we have mv squared over r is equal to product of the charges 4 pi epsilon naught r squared. Okay, that's just centripetal force provided by the electromagnetic force there, electrostatic force. Okay. And this is going to be an argument over the energy, because as we dial in the field, Faraday's law is actually going to give a kick to this thing. Okay. So the kinetic energy is 1/2 mv squared. So we just multiply through by r and divide by 2. So we have 1/2 q, capital Q, 4 pi epsilon naught, 1 power of r. Okay. So that's the initial force law and the initial kinetic energy. So after the B field is dialed in, we're going to add a force term from the Lorentz force, and we'll have a new kinetic energy as well. So let's go ahead and erase this here. After introduction of the B field, is dialed in. How about we call it that? I'll just write just introduced. The idea is that we turn it in slowly. Okay? It gradually appears. So then what do we have? We have the magnetic force minus Q V cross B. If you do your geometry up here, that counterclockwise orbit, and the B as directed here, V cross B would be pointing out, but with the minus sign it's pointing in. So it's attractive. Attractive, just so we're clear on the direction here. So we've introduced that. Now what do we have? We have m v1 squared over r1, because the speed and the radius have, principally speaking, they've changed. Okay. So now we have QQ over 4 pi epsilon naught R1 squared plus this, since we're just looking at the magnitude, Q V1 B. Okay. So that's the new force. Centripetal force, applied force, both of them pointing towards the center. And the new kinetic energy, again, just divide by 2 and multiply by R for both of these terms. So now we have 1/2 product of the charges 4 pi epsilon naught R1 plus Q V1 R1 B also divide by 2. So now we have T initial and T final. And now we'll write the delta T. Am I writing delta T or DT? Let's consult. Well, first I'm doing it step by step. So T1 minus T. Yes. T1 minus T. If I can give myself a little room up here, because I had a step right after that. T1 minus T is just equal to this 1/2 4 pi epsilon naught. And I've got 1 over R1 minus 1 over R. Okay. So I've subtracted off this original, and then I still have this one left, plus Q V1 R1 B over 2. Okay. So here's where we're going to do these interesting steps. We were dialing in a small amount of magnetic field. We were dialing it in slowly. So we're going to take this as an infinitesimal dt, and then I've got a 1/2, so this factor doesn't change, QB 4 pi epsilon naught. And here's what we're going to do is common denominator, so we'll end up with R minus R1 divided by R times R. R1 times R. And since they're close together, this is going to be a minus dr over R squared. And in the same way, I'm going to discuss this thing here as being Q VR dB divided by 2. Okay, because now we're dealing with the infinitesimals. That's kind of the process of dialing in the magnetic field and what happens to it. And here's what we're going to do. We require, to prove that the radius stays the same through this operation, we require specifically that dr be equal to 0. But the way we'll prove that dr is equal to 0 is to prove that the change in kinetic energy is actually equal to what's over here, okay? So I'll put it in a sense, we required, we proved that dr is equal to 0 by proving that these two sides are equal. So that is our task. Now I'll free up a little space. Good. Keep this picture, it's still germane. Okay, so what next? How about this dt right here? We can say now d kinetic energy is d 1/2 mv squared is equal to mdv. Okay. And that's what we're trying to show is equal to Q VR over 2 dB. Now, how can that be? This is what we're trying to show. If we can show this, then we've shown what we had to show. So we are now going to bring in Faraday's law. We refer to this picture again. There we're taking the integral form, so E dot dl around that circle is equal to minus d phi dt, where that's the magnetic flux through the circle. Okay, so the E dot dl, and we're going to have it in the direction. Actually, the directions are going to work out. This is a minus charge, so the E that we get is actually going to be opposite the direction of motion, right? But that'll work out. So if when we analyze this, we're getting E times 2 pi r. Okay. These are just the magnitudes. I'll keep the minus sign here. We can work on the directions. So that's going to be d dt of this pi r squared of b. Okay. Now, any change in r would be infinitesimal. The differential refers to the magnetic field. So we'll have a pi r squared dB dt, and we can now solve for E is equal to, pi goes away, divide by 2, divide by r, it's going to be r over 2 dB dt. Okay, so that's going to be the electric field, and now we're actually ready to get this thing let's see if we have enough room here. So now what do we have? We have let's start over here. But m dV dt, this is just a tangential force, so we're not putting a vector on it. M dV dt is equal to QE. So I'm just going to do the magnitudes here for now. Is equal to QE is equal to Q R over 2 dB dt. Oh, got a mistake here. Good, I caught that. This differential was 2mv/dv, and they canceled the 2. So this was mv/dv. And that's why we canceled one of those speeds. I knew I was missing something over there. So this is what we had to show, okay? mdv is qrdb over 2. And this is what we actually have. Okay. So I can cancel the dt's for both sides, and now I have mdv is equal to qrdb divided by 2. So that's what we had to show right here. And let's make that an implication, because I canceled that thing. It's no longer an equality, right? But be that as it may, we're good. mv/dv QVR dV over 2. Cancel the V's there, that's MdV. Okay, so it's kind of a long way to the punchline, but you see a lot of interesting things came into play here. Now, the directions, I just made short work of the directions here. Let's see if we actually have that. So this is a surface, it's oriented up, therefore E dot dl would be positive if E were in the direction of my arrows, okay? But I've got a minus sign in front of that, so the actual E is in the other direction, which is fine because this is a negative charge, so that it's being driven in that direction as well. So the signs work out. So this is actually a good problem. You can analyze all these aspects. I'll say this once more. We've got the profile here, but I think it's clear. This is closer to us, that's further away. So if this is a positive orientation, okay, and we're going counterclockwise in our integration, then the surface normal is pointing in the direction of my B field that I started there, okay? And the change in flux came about from introducing the red vector in the up direction. Therefore, with that minus sign, I may as well leave it here as well. But I was just working with magnitudes, but the signs are working fine as well, okay? At this point, it doesn't really mean anything because I don't have the directionality on the left there, just magnitudes. But be that as it may, the signs also worked out. So there you have it. Interesting problem. Let's see, I think we're gonna leave it at that today. Okay, so we'll leave it at that today, and next time we're going to, first of all, I'll tackle any problems that you guys want to see discussed here, but we're heading towards proving the laws of optics using electromagnetic wave theory. Okay, good. See you guys next time.